Welcome back, AP students. This next unit that we're going to be covering is going to be going over the ideas of momentum and torque. We're going to be starting out with momentum first. So momentum, you have an idea of what it means. If something gains a lot of momentum, it's gathering speed, it's getting support, it's getting harder to stop. And that's what momentum is. It's basically how hard it is to stop something. So if we were to look at what would make something, really difficult, an object really difficult to stop? Well, one, if it was moving quickly, okay? The other is if it would have a lot of mass or inertia. So if you had a really massive object that was moving very quickly, it would be very difficult to stop, such as a railroad train. So an object with a lot of mass moving very quickly has a lot of momentum. So those are the things that are going to go in our momentum equation. The symbol for momentum is P. I know that may not make sense, but that's because I believe it was Franklin who was experimenting with the idea of momentum, and he called it progress. So anyway, this is named for P for progress, for one of the original ideas about it. Plus, M was already taken with mass and mega and what other M's that have taken it up. So anyway, so as we said, it would have the two factors that we just discussed in it. It has the mass of the object, M, and the V, the velocity of the object. The units on momentum are kilogram meters per second. There's no fancy nickname like there is for kilogram meters per second squared, which is a Newton. There's no nickname for it. It's just kilogram meters per second, so it is what it is. So are there any vectors on the table here? Is mass a vector? No. Is velocity a vector? Yes. Okay. Would it make sense for momentum to have a direction, for it to be a vector? Sure it would. Okay, and so since velocity is a vector, so is momentum. And the momentum vector is just the same direction as the velocity vector. Also restated, an object's momentum is in the same direction that it's moving. So that makes enough sense. So this equation looks a little bit like our equation for kinetic energy. It's got both have mass and velocity in it, but they do mean different things, and they're used for different reasons. We don't have anything squared, and we're not dividing by that 2 and that sort of thing. So what would be the momentum of a 10 kilogram object moving to the left at 20 meters per second? So M is our mass, that's 10, times 20. Why do you think I threw that moving to the left in business? Probably because we should make that 20 negative, so it would be 10 times minus 20, so it would be minus 200 kilogram meters per second. Okay. What would happen to the momentum of a cannonball if the speed was tripled? What would happen to the momentum? Well, since it's just mass times velocity, if you triple the v, you're going to triple the momentum. I was just noticing that I don't actually have an answer that's correct on here. That's okay. It's a trick question. What would happen if I had an object traveling at the same speed but I tripled its mass? Okay, it's going to be the same thing. So that's going to be answer F is tripled. So ignore that. What is the momentum of an 1,200 kilogram elephant at rest? The key word being there at rest, which means our velocity is 0. And if our velocity is 0, so is our momentum. So how do you change the momentum of an object such as a car? Well, you got to get it moving. And how do you get it moving? You must apply a force. Okay, you get it to accelerate. You get it moving. Okay, so if you what two factors are going to determine how much the momentum of an object changes? One is the magnitude of the force. So the bigger the force you apply, the bigger the change in momentum. Okay, so this object that I have that I apply a bigger force to speeds up more, therefore it has a greater change in momentum. So the magnitude of the force. The other thing is, or another thing, is how long that force is applied. So if you look at the top one, I don't apply that force as long, it doesn't end up speeding up as much as the other one that I apply the force to. So This brings into play the idea of what's called an impulse. An impulse is equal to force times time. Okay. And there might actually be a symbol for impulse. I think it might be a J, but we're just going to use impulse. Equals force times time. Your equation sheet doesn't mess with it, so we're not going to mess with it either. And the big kind of overarching idea here is that impulse equals the change in momentum. So impulse equals change in momentum, and I'll show you that a couple different ways before this is through. Okay, so what we're going to do is we're going to take F equals ma, Newton's second law, and we're going to convert it into what we just talked about. So what's the definition of acceleration? It is the change in velocity divided by the time. Right? A equals delta v over delta t. So if we plug that in for A, for acceleration, we get force equals mass times change in velocity over time. If we multiply by delta t, what we get is force times time, which is impulse, equals our change in momentum, m times delta v, which is another way of writing p2 minus p1. Okay, I'll go ahead and show you that this is the same thing as change in momentum as well, but that's the quick and easy impulse equals change in momentum derivation. F is the applied force, delta t is for how long that force is applied, and m is the mass of the object, and delta v is the change in velocity of the object. So let's go ahead and substitute out v2 minus v1 for delta v, and we get F delta t equals m v2 minus v1. Let's go ahead and distribute that m. We get mv2 minus mv1. Now this m times v2, that's going to be my final momentum, and m times v1, that's going to be my initial momentum. So substituting that, or plugging in delta p for that, we get F delta t equals delta p. So there's a couple different ways you can write this equation, or more than a couple. There's several different ways you can write the equation, but they all basically mean impulse equals change in momentum. This is what's on your equation sheet for your AP equation sheet. P equals mv. Okay, so momentum equals mass times velocity, and this right here, delta p equals F delta t. And they are saying that these are vectors, both the momentum and the force and the velocity are all vectors and have direction. So this is on your equation sheet. So any force that exists is applied over some time frame, which means it delivers an impulse. Even things that happen very, very quickly, for example, a tennis ball bouncing off a tennis racket, you can see the strings are stretching here as that ball is being decelerated and then reaccelerated the opposite way. I really should get a better picture, but when you drive a golf ball, that ball looks like it whacks away almost instantaneously, but that ball is deformed severely in the process, and that's the time over which the impulse is applied. Here's a racquetball bouncing off a wall. You can see it forms some interesting shapes as it's doing so, and here's the time frame over which that's occurring. Very small time frames, but time frames nonetheless. Here's a water balloon that's bursting on the ground, just about ready to burst. Again, it happens very quickly, but it does take time. So when you play a sport, let's say you play baseball, your coach is going to tell you two things to get a good. Well, he or she is probably going to tell you a lot of things, but as far as how to hit the ball far, there's two things that are probably going to be on that list. One is to hit the ball hard. Okay, so we want to change the momentum of that ball. That ball is coming towards you. You want it to stop and then go the opposite direction. So that's a big change in momentum. So you want to hit the ball hard, duh. Okay, so that's F, and then we need the delta t. So how do you maintain that force for a longer time? How do you keep that ball in contact with the bat? for a longer period of time. You follow through. Okay, that's why your coach is always saying follow through. And little did they know they were saying, maybe they do know, I don't know. F delta T equals delta P. Impulse equals change in momentum. So told you I said I would. Okay. So let's say we've got a car and it's driving 60 miles per hour. Let's say it can come to a stop two different ways. One, it can drive into a brick wall and stop very, very quickly. Okay, that's option one. Or two, it can apply its brakes and come to a stop much more slowly. Okay, which has the greater change in momentum? The one that went from 0 to 60 quickly, or the one that went from 0 to 60 slowly? Or is it the same? Well, they both have the same initial momentum, and they both have the same final momentum. That means they both have the same change in momentum. Okay, so they both have the same change in momentum, but there are some differences. Even if they have the same F delta T, the same impulse, okay, if we want to come to a stop very, very quickly with a small delta T over a very short period of time, that requires a large force. However, if we want to come to the same change in momentum, if we apply a small force, we have that come to fruition over a larger change in time. Okay? So short time, big force; long time, small force. Okay. All right. So let's say you're on your roof and you need to jump off your roof and you want to do this safely. So what you do is you jump off the roof and you lock your legs and you land on the ground stiff-legged vertically. That's obviously how you want to come to a stop from your jump off the roof, right? No, that would be bad. What you might want to do, because you would come to a stop very quickly, but that would require a large force, just like the car crashing into the wall required a small time, requires a large force. You want to bend your knees and roll, extending the time over which you're slowing down, maximizing your time, which minimizes your force. So if you've ever heard the term rolling with the punches, if you ever get punched, there's two ways that you can approach this. One, you can lean into the punch, okay, and bring his hand to a stop very quickly. Or you can roll back with the punch, okay, so that you bring his hand to a stop over a greater period of time. So if you roll with the punch, as it said, you roll backwards with it, you extend the time of contact with the fist, but you decrease the force of the fist. Okay. If you drop an object on concrete versus so this would be concrete and this would be some sort of fabric. Why is it much more likely to break on the concrete than the fabric? Well, there's a couple different reasons, but one of which is that when the glass falls into the fabric, it deflects, it depresses the fabric. It's like the strings of the tennis racket we saw, where it bends them back. It'll deform, and in deforming, it's extending the time over which the glass is slowed to a stop. So again, extending the time decreases the force, as opposed to coming to a stop very, very quickly with the concrete not deforming at all. There's also the fact that in deforming, it's also cradling the shape of it and increasing the area of contact over which the force is applied, which decreases the pressure, as it's said. So there's also that factor too. Again, there's lots of instances where you want to extend the time and decrease the force of contact. Airbags, your face, if you come into a crash, your face could hit the steering wheel and come to a stop quickly, or your face could hit an airbag and come to a stop still very, very quickly, but more slowly than hitting the steering wheel. Bungee jumping. I've got this idea for bungee jumping. I think that those bungee cords wear out too fast. So what I'm going to do is, with my bungee jumping business, I'm going to save money in the long run. It might cost a little bit more up front, but no, probably not. I'd probably save money up front too. I'm gonna use steel cable. So I'm gonna tie steel cables around your legs, and then have you jump off the building. And then you know, there'll be that whole deal. You'll come to a stop a little bit more quickly, but that won't do anything, will it? Right? Of course, that'll be a problem. So the bungee cords slow you much more slowly than the steel cable would. So it reduces the amount of time. Okay, so just a similarity between this unit and last unit. Another similarity. Before we had work equals the change in energy. Here we have impulse equals the change in momentum. Okay, similar but different. Okay, and these are both on your equation sheet. Although I don't know if this one is per se, but work, the formula for work is, and you should know that work equals the change in energy. So let's work a problem or two. We've got El Nino rolling along the floor at 2 meters per second, let's say to the right. Stops and hits a wall. What's the change in momentum? Okay, and what's the impulse? And what's the force involved if that is the time? So we've got El Nino rolling to the right, so it comes to a stop. So that tells me that my final momentum is 0 if it comes to a stop. My initial momentum is 6 and positive 2 meters per second because we're rolling along to the right. So 0 minus 6 times 2 gives me minus 12. So that is my change of momentum is minus 12 kilogram meters per second. The next question is, what is the impulse? Okay, if I ask you this on a test, and you know the change in momentum, impulse is the change in momentum. So don't forget that. So that answer is just same as the above. And the next question is, what force did the wall exert on El Nino? El Nino is my bowling ball, by the way. I don't make a habit of naming all my inanimate objects, but El Nino came pre-named, so I just roll with it. Yeah, that was pretty bad. Anyway, so if El Nino hits the wall and comes to a stop in 0.05 seconds. Okay, so we know the impulse is minus 12, so that's equal to force times time. Okay, because that's our change in momentum. Impulse equals change in momentum. Minus 12 equals the force times the time, which is 0.05 seconds. And we get negative 240 newtons. What is the significance of the negative on the force? Well, if El Nino was rolling along to the right, the wall exerted a force on El Nino to the left to get it to come to a stop. So that is why the negative is there. So that those vectors actually do make sense. We're back to vectors as opposed to energy, which was not a vector quantity. So let's say I wanted to figure out the change in momentum from a graph. Sometimes the AP exam will throw graphs, probably in a multiple choice question for you. And they say, what's the change in momentum? Well, we know that impulse equals the change in momentum, and change in momentum equals force times time. We have a force of 100 newtons times 10 seconds, so that would be 1,000 Newton seconds, which is also, I told you there was no abbreviation. There is a sort of an abbreviation. It's a Newton second. So, sorry, I didn't mean to lie to you. I forgot about that one. 1,000 Newton seconds. So, and really what we did is we found the area under the curve. Strangely enough, again, the integral has a use in physics as well. Again, if you had this question and they said what was the change in momentum, you would just find the area under the line, and that would be the change in momentum. So I could see a multiple choice question like that if they had multiple choices here. Which has the greater change in momentum, a ball that hits a wall and comes to a stop, or a ball that hits the wall and bounces backwards? Which one has the greater change in momentum? Or would it be the same? What do you think? If you said the one that bounces back has a greater change in momentum, you would be correct. Okay, let me show you why. So let's pick some easy numbers. We've got a ball that's got a mass of 1 kilogram, and it's traveling at 1 meter per second to the right. Okay, comes to a stop. Okay, so my final momentum is 0 because it comes to a stop. My initial momentum was 1 times 1, so then I'm going to subtract that. So 0 minus 1 times 1 gives me a change in momentum of -1. Okay. If we look at the ball that bounces back, okay, well, its final momentum in this case, it has a negative velocity because it's traveling to the left, okay, in the final scenario. So it's negative velocity times its mass of 1 gives me -1 minus the same initial momentum, which is 1 times 1. So it's that negative velocity that gives me -2. So I actually have twice the change in momentum bouncing back, and that kind of makes sense. So first you've got to bring the ball all the way to a stop, and then you have to accelerate it back all the way to its initial velocity in the opposite direction. So it kind of makes sense if you think about it. Let's work a problem here. We've got a .540 kilogram baseball pitched at 54 meters per second and hit back towards the pitcher at 75 meters per second. How long was the baseball bat in contact with the baseball if the average force was 850 newtons on the ball by the bat? Okay, so given the unit we're in, we're talking about forces, and we're asking about time. So there's a good bet we're going to use F delta T or FT. You can leave off the delta. F times force times time equals delta P. So once if I know the delta P, I know force times time. So we want to solve that first. So P2 is our 75 meters per second to the left. Okay, it bounced back, so that's going to be in the negative direction. So that's -75 times 0.54. Okay, minus my initial momentum, which is positive 54 times 0.54. Okay, so I'm subtracting, I've got a negative number and I'm subtracting a positive number from that, and I get -69.7. So that's going to equal F times T. It tells me that the baseball bat exerted a force of 850 newtons, okay, on the ball. How long was it in contact to affect that change? And so we solve and we get 0.082 seconds. So not a whole lot of time. It is a very quick event. Okay. All right, and that is it for the day. Note-wise, you can work on the problem.